plus de batterie. Attends, une seconde. J'oublie les piles. Non mais on va bien pouvoir trouver des piles. Normalement là, on devrait avoir du son. On a du son. Ouais, et là normalement tu vas me dire si tu reçois du son maintenant. Ouais, ça devrait pas tarder. Ok, nickel. Bon là je parlais quand même relativement dans le micro, mais on va faire un test avec lui. Tu peux mettre le micro s'il te plaît?
Ouais, alors je le mets où?
Là tu m'entends? Ouais, pourtant là moi je suis assez loin.
Je le mets où, à quelle hauteur à peu près?
Ouais,
tu veux que je le mette sur la cravate, c'est bon?
Ouais.
Hop.
Après je te laisse.
Ok.
Ça va peut-être plus simple en fait que tu le fasses passer par en dessous. Ouais, une seconde. Que tu le fasses passer, tu sais, par.
Bon, attends, on va faire un test comme ça parce que je vais aller aux toilettes quand même avant.
Ouais.
Ok. Tu m'entends bien?
Faut que tu nous dises si t'entends bien.
Est-ce qu'il m'entend bien là? C'est bon? 1, 2, 1, 2.
Il y a 10 secondes de délai.
Ah, il y a du délai?
Sur le streaming, ouais.
D'accord.
Ouais, ne t'inquiète, il va même pas le prendre du tout.
De quoi?
Ok, bon, c'est bon, ça marche bien. Hop.
Ok, c'est bon. Batterie, t'es bon? Est-ce que tu m'entends là? Ok, impeccable. Bon, j'ai quand même un peu de fil qui se balade. On peut le... s'arrête ce truc. Ok. J'ai le fil qui se balade.
Dans la poche.
Ouais, je vais le mettre dans la poche. Hop, si je peux. Ouvrir.
Je t'aiderai pas, mais...
Olivier. Là, voilà.
Dans la poche devant, hein.
Ouais, je vais le mettre derrière, ça va pas mal.
Tu vas parler... tu peux essayer de parler au volume dont tu vas parler si tu veux.
Je sais pas. Qui c'est qui est... Jamel, tu m'entends? Ouais. C'est bon, c'est nickel ou faut que je parle plus fort? Non, c'est bon. Ok. Bon, voilà, ça devrait être à peu près ça. Okay. Essayer de parler à ce niveau sonore. Ok, c'est bon? T'as un retour sur qui reçoit et...
Excuse-moi, t'as dit quoi?
T'as un retour sur qui regarde
J'ai un retour en nombre de vues, mais du moins pas là, mais mon collègue peut l'avoir. Mais moins, mais de qui regarde. Vu que c'est sur YouTube, on n'a pas de... En gros, merci. En gros, il a aussi des pubs de secours, t'en as là?
Non mais c'est pas des comme ça, hein. C'est des modèles plus petits que moi. Non, pour toi c'est bon, non c'est pour moi.
Ah, dans l'émetteur?
Pour le pointeur, non pour le pointeur.
Le pointeur...
Bah, j'en ai. Et normalement il n'y a pas de raison.
Et au pire, je t'ai ramené ça.
Tu m'as ramené quoi?
Non, tu fais en micro dans le
Ouais.
Tu le fous devant toi.
Bon, ou sinon on peut le mettre là.
Ouais, on le mettra au milieu.
Devant.
On va le faire direct en fait.
Bah ouais, tu peux parce que c'est le président qui va commencer. Je sais déjà faire le nœud de cravate, m'en demande pas trop. De quoi? Elle n'est pas censée pointer mon engin non plus.
Bah si, là.
Si, quand même. À quoi ça sert sinon?
Bah, je peux pas plus de toute façon. Mais elle est bien, c'est bon.
Bah oui, hein.
Hein? Ouais.
Le Mac il est chargé?
100%. Mac chargé, PC de secours au cas où que. Ouais, je vais le prendre. Il y a un mot de passe ou?
Bah oui, il y a un mot de passe.
Là, tu descendras. Tu feras coucou à la caméra. Ouais. Ah, ouais, j'ai totalement oublié. Va le chercher.
Oh bah non. Allez, je mets un peu de vodka dedans.
J'aurais dû mettre une bouteille de liqueur sur la table.
Et je l'ai déjà en plus.
Quand on a pris d'eau?
Bah comme ça, on fera chacun un croisé.
Non, je veux pas savoir. Regarde pour toi. Ouais. J'avais peur que t'aies pas de VGA dessus. Hop.
Tu veux savoir? Vous inspirez le respect, et non la jalousie. Pour quelle raison? Eh bien parce que vous êtes juste, tout simplement.
Je commençais comme ça. Mon horoscope est très bon aujourd'hui.
Ta santé est excellente.
Écoute, quoi de mieux? Ça va, mon madame?
Oui, là du coup j'ai un peu de merde.
C'est bon? T'as besoin d'un retour?
Non, mais je voulais savoir s'il y a un jury ou pas.
Bah, le jury... c'est sûr que si je branche pas le micro, ça risque pas.
Ouais, c'est toujours comme ça. Les scientifiques, ils sont super bons en scientifique et puis en langue, ils sont bien.
De la preuve.
Et du coup,
Bon, il y a tous les gens d'ICAR. Non, je pense d'ICAR, il n'y a pas grand monde en fait. d'ICAR. Non, Sylvie, elle est en rendez-vous médical. d'ICAR, il y a Fabien et Zénep. Et puis. Non, elle n'est pas là. Peut-être ce soir, faudra que je l'appelle, excuse-moi. Non, bah d'ICAR, il n'y a personne. Après, il y a plein de gens qui m'ont envoyé des mails, parce qu'il y a eu les inondations là, et du coup, tout ce qui est réunion, machin, les routes sont bloquées, donc les gens se déplacent pas, ils font des vidéoconférences ou des téléphones groupés, quoi. Ils s'appellent sur un serveur, ils discutent tous ensemble, donc j'ai reçu encore des mails là de gens, bon, désolé de pas être là, réunion, machin, si, ça. Donc, ouais. Bon, c'est normal. Hein. Bon. J'espère qu'on va pas être dérangé par tous les camions et les mecs là qui arrêtent pas de faire des allées et venues.
ah oui, mais en même temps, ils emménagent le hall Darcy. Donc,
Quand aujourd'hui là
je sais pas si c'est aujourd'hui ou demain.
Ça y est, il est livré là?
Bah, il est fini, hein, ça y est.
Oui, mais est-ce qu'il est livré? Est-ce qu'ils ont les clés et tout?
Je crois que Dashnar a récupéré les clés. Il faudrait demander à Delphine Belon.
Ah, c'est bon le fil? Bientôt toi, Mehdi. Ah, t'as refermé? Cool. C'est sûr. Certes. Je sais pas. Non, il n'y en a qu'une. Hein. Il n'y en a qu'une, il y a juste un retour de presse et la caméra qui est là avec une possibilité de suivre, quoi. Ouais, non, mais bon, en plus, on m'a montré ce matin, il contrôle la distance et tout, là. Nickel. Tip top. On aimerait bien avoir du matériel comme ça.
Regarde ta bague.
Oui, je garde ma bague. Bon. Hein?
Par contre, évite de la trifouiller quand tu fais tes présentations. C'est pour ça que je te dis tu gardes ta bague.
Si je trifouille, c'est que je suis énervé.
Bah oui, c'est pour ça.
Et je vais avoir le pointeur dans cette main-là.
Ça va aller.
Vous me dites ça va aller, mais c'est vous qui êtes en train de stresser, là. Vous me stressez, en fait.
Ah bah moi tu me rends toi qui me stresse. Je voulais dire à maman, je sais pas essayer de lui dire.
Tu te laisses à patienter là. Hein,
Ouais,
Non, mais attends, tu m'as pris des choses cette moi, elle est plus ma derrière.
Les autres, c'était pareil.
Ouais mais là.
Les autres, c'était
Faut
pas.
vraiment que tu t'achètes. Non, ça
Non,
va
ça
pas.
se voit.
Faut vraiment que tu achètes des noirs en fait.
Mais j'en ai des noirs.
Ah, bah j'ai beaucoup raison, hein.
Bah, elles montent jusque-là. Je vais avoir trop chaud, là.
T'as qu'à te mettre pieds nus.
J'ai déjà chaud.
Pourquoi t'avais parti des petites comme ça?
Mais oui, je voulais mettre les tongs.
avec un costume, ça aurait fait un peu de
Non, short et tongs.
Voilà.
Hein, derrière, je... Et pas que t'aurais mis des tongs.
Ramener des chaussettes de contention, là t'aurais mis.
Oh.
Hein, derrière les tongs, ça se serait pas vu, hein.
Bah oui, parce que tu vas être debout. Hein.
Ouais.
Laurence, on a vu votre élève, puis elle a dit ah, elle a des petites chemises blanches et tout, elle est toute belle comme des filles. Je dis ouais, mais moi je suis encore plus belle. Laurence,
Il y a le micro. Non, mais tu parles. Il y a le niveau vert là.
Oui, je sais. Mais je l'avais pas vu. T'as qu'à l'éteindre.
Ouais, mais pas le temps, c'est bon. Ouais. Ouais, ouais. J'ai faim.
Non.
J'ai faim, j'ai soif. Bon, il y a meilleur après. On fait tout le monde à la même enseigne. Déjà que je suis un peu vénère parce que tu as vu, j'ai mis des calepins Prisme. J'en avais 8 sur mon bureau. Il y en a 2, enfin il y a Dibble qui m'en a pris un hier et là j'en ai encore un qui a disparu quoi. Donc bon, ça fait un peu con quoi. Bon, tant pis, faire avec. Hein. Je les ai pas tous vus. Bah, j'ai vu Dibble hier matin. Il est arrivé lundi soir.
Oui, il est passé chez nous.
Et hier, tu m'as vu hier. Enfin, tu m'as aperçu. Et en fait, je l'ai vu hier matin. Je discutais un petit peu avec. Bon, voilà quoi. Et puis à midi, à 1h, t'as fait Fabrice qui m'appelle. Il me fait Martin Tuner. Il est sur le campus devant les bancs moteurs. Tu peux aller le rejoindre et tu mets le tuner. Martin Tuner. Et du coup, en fait, non, il n'était pas là ici sur le campus. Il était à Icar, devant Icar.
Et il était devant quel banc moteur à Icar?
Mais il n'y a pas de banc moteur, alors je sais pas. Non, mais c'est Fabrice qui a du mal à comprendre. Et il était en train de manger à la terrasse avec Dibble. Alors du coup, il me dit tu peux me le récupérer, tu me le donnes. Finalement, il était avec Philippe. Je reçois le message au moment où j'arrive à Icar. Je fais je vais aller dire bonjour à Philippe et puis lui dire bonjour, me présenter et tout. Et c'est pour ça que je suis arrivé à Icar. Du coup, gros coup de panique, pendant 1 heure. Non, et puis Louis, le premier rapporteur, il est arrivé ce matin.
Ouais, il vient de Nevers, donc ça c'est simple.
Nevers, il n'a pas dû avoir trop de problèmes. Et les autres, Antonio Pires da Cruz, il vient de l'IFP, alors je sais pas comment il est venu. J'imagine aussi, ouais, mais je pense.
Ça continue encore?
Le train en plus avec les grèves.
Ça continue en fait.
Mais alors j'ai pas compris parce que apparemment le direct il met une demi-heure de plus en ce moment pour faire Austerlitz, Gare d'Orléans ou les Aubrais.
Il y a à côté de Bretigny, il y a eu des inondations.
Ouais, c'est ce que Fabrice me disait.
Je crois qu'il roule doucement.
Plus le fait aussi qu'il y a peut-être les grèves, j'ai pensé. Parce que ce matin ils ont dit qu'il y avait pas les TER, les intercités, il y en a 7 sur 10 qui circulent.
De toute façon, le soir, ça va, il pourra retourner s'il a pris le train.
Je sais pas ce qui est prévu, s'il reste un petit peu après, s'il repart direct, je sais pas. Et puis Francesco, je crois qu'il devait arriver à midi à peu près, donc non, je l'ai pas encore vu. Enfin, ces deux-là, je les ai pas encore vus du coup. Voilà. Puis Guillaume est absent du coup. Il est en train de se dorer la pilule à La Rochelle. De toute façon, le temps qu'ils arrivent, il va être demi. Je sais pas. Mais à chaque fois que le restaurant il est réservé à la terrasse, même s'ils y vont à midi, je trouve qu'il y a toujours du retard. Et si ça se trouve, ça va être. S'il y en a un qui est arrivé à 13h, je sais pas, il suffirait qu'il y en ait un qui soit arrivé à 13h. Du coup, ils mangent tous ensemble. Ça traîne. Après, ce qui est un peu bête, c'est s'il y en a un qui est venu en train, qui doit repartir en train, qui a son train à telle heure, t'as pas trop le temps de discuter, ni de.
Oui, il poserait ses questions.
Il doit participer à la délibération quand même.
Il reste ce soir.
Bon, j'espère. J'espère qu'il reste un petit peu avec nous. Hein.
Et puis lui, c'est facile, il a dû prendre sa voiture.
Mais je sais pas, ouais. Je sais pas. Moi, je l'ai vu arriver avec. J'ai vu sa valise. Sa petite valise. Hein? Ah bon, tu trouves?
Un tout petit peu.
Ouais, un chouïa si tu veux. Ouais, j'ai sommeil, ouais. Je dors pas beaucoup les nuits et hier soir, je me dis, je fais un repas avec ma mère, là, puis la famille. Et, enfin, au final, on s'est couché quand même 11h30, quoi. Puis, ouais, c'est un peu de mal à m'endormir, quoi. Dormira ce soir. Non, c'est bon. Le tout. Le T'es au courant ou...
Tu fais pas un post-doc après?
Si, non, mais non, mais des fois que Philippe ou Guillaume en auraient parlé.
On n'en a pas parlé, c'est pour ça que
Non, je vais peut-être partir avec. Enfin, rejoindre Dibble au Coast.
Ah bon?
Et travailler avec Bent Johnson.
Ah ouais, d'accord.
En fait, Bent, il est parti, il a quitté son labo. Ouais, il a quitté son labo en Suède.
Oui.
Il a pris ses clics et ses claques et donc il est là-bas, il essaye de remonter des bancs moteurs là-bas. Et en fait, donc il m'a dit je veux faire comment il m'a nommé ça, un world class, je sais plus quoi, enfin une entité à l'échelle mondiale, représentante à l'échelle mondiale sur la combustion automobile. Et du coup, il veut monter des bancs moteurs et tout. Pour le moment, il est tout seul.
Donc c'est en Arabie Saoudite que tu dois aller.
Ouais. Donc là.
Ça paye bien.
Bah, il m'avait proposé plus Bent et finalement j'ai moins, mais bon, déjà ce qu'il me propose, on va pas se plaindre, quoi. C'est déjà plus que ce que j'aurais trouvé en France, quoi. Donc ouais, il n'y a pas... Et sans taxe surtout.
Je sais pas qu'il était à...
Et puis free housing. Et assurance santé, médicale, tout ça.
Et logement?
Ouais, logement ça. Ouais. Donc juste...
Donc en fait, c'est de l'argent de poche.
Bah, pour te nourrir et profiter, quoi.
2 heures, c'est bon, ça.
Bah non, mais j'ai vu sur des photos qu'il y avait une réserve de corail là-bas, de coraux. Et enfin, la mer est belle, ils font des études scientifiques là-bas, donc ouais, peut-être que j'essaierai la plongée.
Oui, ça doit être sympa.
Ça doit être sympa. Donc je verrai. On va voir.
C'est un bon plan.
Ouais. T'as des... Comment... T'avais 20 minutes. T'es venu pour rien, quoi. T'es venu juste pour le plaisir, quoi. Le téléphone, il est en silencieux dans mon sac. Hein? De quoi? Ok.
Parce que sinon, je suis pas dans aujourd'hui, je pourrais pas te. Si j'ai des photos et puis dans les délibérations, et si je suis pas dans l'entier, je peux pas savoir quand est-ce que c'est. Ok. C'était juste ça. Moi, mais aussi, j'en suis dessus. Ça va?
Ouais.
C'est chiant.
Fatigué.
Fatigué.
Je fatigue déjà.
T'as encore rien fait. C'est chiant, on se met quand même juste 2 heures, on arrive 25 minutes de retard. C'est un peu respectueux. C'est d'être à l'heure.
Il y en a peut-être un qui a une indigestion.
C'est bien, c'est ta famille.
Bon. Bah, je sais pas, bah, tu sais, à midi, ils étaient pas tous arrivés. S'il y en a un qui est arrivé à midi et demi, 1h, le temps qu'ils mangent, qu'ils aillent jusqu'au café. Comment? Voilà, le temps qu'ils refassent le monde, qui parlent de discussions hautement scientifiques et de collaboration. Ils se font un gros câlin tous ensemble. D'ailleurs, Sandrine, il en est où, Kevin, en ce moment? Encore? Ok.
C'est un peu ma baisse matin.
Il va se passer quelque chose.
Ces filles, ils étaient à l'heure. pourtant, c'était aussi des gens. C'était aussi des gens. Et ils étaient 300.
C'est beaucoup plus light.
Bon courage.
Bah, je te remercie. Hein? Ça se trouve, il va faire un gros. Je vais faire à Philippe, bah, on commençait à se dire on va peut-être annuler. Attends, déjà qu'ils ont eu du mal à trouver une date.
Ouais, ah bah oui, là, ça a pas été très.
Attends, au début c'était vers le 20 mai.
Ouais.
Ils ne trouvaient pas une date. Après ils ont dit début juin, ils ne trouvaient pas une date. Fin mars. Ouais, fin mars.
D'accord.
Fin mars. Bah, normalement il aurait dû avoir 2 mois, mais on a poussé un peu par rapport aux dates de l'école doctorale, parce que la réunion de l'école doctorale pour validation, elle a eu lieu là lundi. La suivante qui allait avoir, c'était là lundi. Du coup, ça me reportait encore jusqu'à la fin du mois, quoi. Donc, ouais, voilà, quoi.
D'accord. Bon. Et c'est vrai qu'il y a du monde qui vient de l'étranger en plus. Trouver une date, c'est long.
Bah, au final, en fait, c'était pas les étrangers. Le problème, c'était plutôt c'était Guillaume et Louis. Parce que Louis avait des réunions, machin, les fins d'année scolaire et tout.
Ah, le directeur de l'école.
Ouais, voilà, surtout. Et puis Guillaume cette semaine, il a l'école de combustion. Et puis, donc, en fait, ils n'arrivaient pas à se mettre d'accord, c'était eux deux surtout. Et bon, du coup, c'est Guillaume qui a lâché le truc, qui a dit, tant pis, je serai absent. Et puis c'est pas grave. Bon. Et puis, pour tout ce qui est cinétique, il y a Philippe. Pour les discussions un peu cinétiques, Philippe est là, donc.
Il n'avait pas s'interroger.
De qui?
Comment ils arrivent. Donc qu'ils soient.
Je te propose de prendre la présidence, histoire de commencer.
Moi, je le sentirais bien, personnellement, mais bon, je n'ai pas été conviée. Hein. Allez.
Ça va?
Oui. Bonjour, Christine. Ouais.
Du coup, tu t'es libéré?
De.
Non, je sais pas. Tu m'as envoyé un mail. Du coup, je me suis dit, elle sera pas là.
Mais si.
Dommage.
Mais si, bien sûr que si. Ils arrivent.
Ils arrivent, tu les as vus? Faut les... Oh. Fabrice est stressé. Pourquoi?
Parce qu'ils sont en retard.
De toute façon, une demi-heure, on a déjà vu, quoi. Hop. Ok. C'est Christine qui a fait le dîner avec moi.
Ah, bonjour.
Ma maman.
Oh, bah oui, ça va.
Attends.
Enchantée.
Non, mais attends, on va. Ok. Bon, ça va. C'est bon, t'as un bon retour de son et tout. Impeccable, ok. Ça marche. Bonjour. Enchanté.
Désolé pour le retard. Mais
C'est pas.
tu y attendais un peu? Non.
Oui, honnêtement, oui.
Honnêtement,
Largement.
oui.
Are you again?
So are we expected to sit in a particular place?
More or less, yes. So, oui, j'attends que...
Okay.
Non, c'est bon, vas-y, va jusqu'au bout.
Jean-Baptiste.
Comment vas-tu?
Très bien et toi?
Ça fait un moment que je t'ai pas vu, toi?
Oui, je suis content de vous voir.
Moi aussi, ça me fait plaisir. T'as un
On
peu
aura
de temps.
discuter après.
Ouais, bien
sûr.
sûr.
En voiture, donc
Bien sûr.
J'ai pas d'horaire. J'ai vu qu'il y avait une tireuse et du buisson.
Ouais. Ah, je t'explique pas les trucs.
Non, mais quand j'ai vu ça, je me suis
Fabrice, tu te mets là?
Ouais.
Je vais donner ça à Louis parce que, en fait, il y en a un, il y a quelqu'un qui me l'a piqué.
Oui, c'est.
Hop. Il m'en manquait un.
I will make it first. Donc Jean-Baptiste, on est réunis pour assister à ta soutenance. Donc le jury que je vais présenter en anglais va t'écouter et ensuite te poser quelques questions. Il y a environ 45 minutes pour faire ton exposé. So the committee is composed of several people coming from outside. I will first of all present the external reviewers, the one who reported on the thesis. Dr. Antonio Pires da Cruz from IFP Énergie Nouvelle, Professor Louis Simon from University of Bourgogne. Then we have two professors coming from outside. Professor Martin Turner from Lund University. Professor Robert Dibol from King Abdullah University of Science and Technology. Professor Francesco Contino from the University of Brussels, the Free University of Brussels. And the two locals, the advisor, PhD advisor, Professeur Fabrice Souchet, et moi-même, Philippe Dago, qu'on a nommé président. On vous écoute, jeune homme.
Très bien. Merci, Monsieur Dago, pour cette introduction. So, thanks, Mr. Dago, for this introduction. Today, I'm going to present you and defend my my thesis works, which was on experimental study of the HCI combustion through the use of minor oxidizing chemical species. So, I will start my presentation by introducing you the context of this thesis works. Nowadays, engine manufacturers have to reduce the fuel consumption of vehicles in order to save fuel due to a future depletion of fossil resources. In parallel, they also have to reduce CO2 emission to reduce the global warming impact of these greenhouse gases. They also need to decrease pollutant emissions in order to improve the air quality and finally continue to improve efficiency of the engines. So, to meet these requirements, there is several solutions. The first one is to replace conventional fuel by other one, alternative fuel, for example. But still, today, we don't know how to oxidize and burn such fuel. Another solution will be to use advanced combustion modes, such as low temperature combustion, LTC. But today, we don't know how to control efficiently such a combustion modes. These two solutions are the central topics of the ERC2GC Safe project. The main aim of this project are to acquire new data using a wide range of experimental setup in order to promote the combustion of second-generation fuels and propose innovative combustion control. This will generate thermochemical and kinetic parameters and help developing kinetic models for modeling and modeling application. In this project, I work in the work part 2 called experimental ignitions, whose objectives are to explore ignition or combustion of different classes of fuels, control the combustion process through active chemical species in order to bring innovative technical solutions and opening new horizons. For this thesis work, I will consider the HCI combustion. HCI combustion is defined as a combination of compression ignition and spark ignition engines. It consists of preparing an homogeneous mixture, like in spark ignition engines. These first gas are inducted into the combustion chamber and then compressed and finally, autoinic like in compression ignition. The overall combustion process of this advanced combustion modes is entirely governed by kinetics, and due to these principles, such an engine may meet the requirements for manufacturer. In this study, we chose to investigate this combustion modes in order to help understanding the homogeneous combustion process which can occur in all the advanced combustion modes. But the main challenge for such an engine are to find efficient control means in order to control the overall combustion process over a wide range of load and speed. So here is presenting a typical heat release rate for HCI combustion. Depending on the fuel reactivity, the combustion can occur with two stages or in one stage. There is several means to control the combustions. Each of them are their own pros and cons, and still today we try to investigate other approach. So, which kind of approach we can use is, for example, oxidizing chemical species such as nitric oxide or ozone. Nitric oxide shows that it can promote the HCI combustion and advance its combustion means. With several hundred of ppm, it can more or less strongly advance the HCI combustions. Another one is ozone. Ozone is a very powerful oxidizing chemical species. We can strongly advance the combustion phasing, as you can see on this graph. And it was also investigated in the literature. Its impact, it can change the fuel structure and therefore decrease the autoignition temperature of fuels. So, compared to nitric oxide, ozone have more impact, and therefore we chose to investigate the use of this chemical species to try to controlling efficiently the HCI combustions. This chemical species does not exist naturally, so we have to produce it. To produce it, we can use an ozone generator. Today, this kind of device become increasingly small, and an integration into a real vehicle could be possible. So the first objective of this thesis work was to evaluate the potential of using such a device and try to controlling the HCI combustion. The second objective was to investigate the impact of ozone on a wide range of fuel, because HCI engines may use is fuel flexibility. So, before discussing the results obtained during this thesis work, I would like to present you the experimental setup and computation tools used during my thesis. First, all along my thesis, I use an engine bench. This is a typical diesel engine with a compression ratio of 16, which was converted into a single-cylinder engine whose the intake has been modified and include a constant volume in front of the intake pipe to prepare a fully homogeneous air-fuel mixture. All the data are recording over 100 consecutive cycles and then analyzed using a post-treatment program developed during this thesis. As our objective is to focus on ozone, we use an ozone generator. This is a commercial device which has to be supplied by pure oxygen in order to produce only ozone in its output. And avoid the production of undesirable species such as nitrogen oxide. This device has been implemented like this on this scheme. the injection of ozone is directly into the plenum in order to maintain an homogeneous charge composed of air, fuel, and ozone, and also to make possible a measurement of the ozone concentration which will be seed into the combustion chamber. As the ozone generator is supplied by a constant oxygen flow, we add another constant flow of pure nitrogen in order to keep the mixture at the entrance of the engines with air, fuels, and a few ppm of ozone. In parallel to our experiments, we perform computations in order to provide kinetic interpretations of our results. The kinetic computations are based on a constant volume coming from the thinking software. It uses a kinetic scheme in agreement with the fuel selected during our experiments. We chose to use initial conditions in agreement with the in-cylinder pressure cycle recording. And finally, we interpret our experimental results by using the results, the emission delays, and a reaction pathway analysis. Now, I'm going to discuss the results about the first objective of my thesis works. To present this result, I will only consider primary reference fuels, and I will present you first the impact of the ozone, then what we have to consider if we want to integrate an ozone generator into a vehicle, and finally a first application. First, about the impact of the ozone. So it was already investigated into the literature, so I present quickly the results for all the primary reference fuel considered in this study. We can observe that the general impact of ozone is to improve the combustion and advance the phasing, as you can see on the shift of the CA50 on this graph. For all the PRF except N-heptane PRF 100, we have the same trends, but primary isooctane is there is an higher effect from the ozone on isooctane. This is due to the intake temperature of the engine, which was tuned near 200 degrees Celsius, while for the other fuel considered, we only use an intake temperature at the ambient temperature. And as the ozone is very sensitive to the temperature, this explains the high effect for isooctane. So, coupled to these experiments, we perform kinetic interpretations of the effect of the ozone. Basically, when there is no ozone seeding into the engines, the fuel, RH, is oxidized with the oxygen molecules. It produces HO2 radicals, and then the radical of the fuel continue to oxidize up to the formation of hydroxyl radicals, OH, which strongly improve the fuel oxidizing and lead to the ignition of the fuel. In the case of ozone, in fact, this is not ozone which improves directly the combustion, but the O atom coming from to the ozone decompositions, which lead directly to the production of the hydroxyl radicals, which lead to the combustion. Therefore, the ozone injection directly and lead to an early ignition combustion of the combustion. So, now, if we want to consider a real applications, what we have to think. From now, ozone generator is supplied by pure oxygen, but for a real application, it will be more suitable to use oxygen contained into the air to produce ozone and inject injected heat into the combustion chamber of the engine. Unfortunately, the presence of nitrogen into the air may lead to the production of NOx. And NOx may also be found into the EGR of the combustion chamber or into the EGR coming from to EGR loop in the case of a wide application range of the HCI combustion. So the objective for this part was to compare the effect of these three oxidizing chemical species and to study the interaction between ozone and NO, which was NO because it is the first nitric oxide produced by ozone generator, and this is the main nitrogen oxide component found into the exhaust gases. For performing the experiments with these three oxidizing chemical species, we propose a new configuration of the engine setup. And it only includes a nitric oxide line to inject NO or NO2, which is diluted into nitrogen. Therefore, we also add an oxygen flow in order to keep the intake of the engine with air, fuel, and few ppm of the oxidizing chemical species considered. Here is presented the in-cylinder pressure trace and heat release rate trace for an injection of 20 ppm of each species, and in the case of not any injection of this species. We can observe that all these species allow to improve the combustion. This is an advance of the combustion and an increase of the maximum pressure. But with this graphic, it is not very. We cannot really appreciate the impact of each chemical species. Therefore, we plot the shift of the CA50 in order to better observe the impact of each species. So this graph confirms that all the species advance the combustion phasing of the engines, and ozone lead to the higher impact and NO2 to the lower. With this result, it is difficult to explain why ozone lead to the higher impact and NO2 to the lower. Therefore, we perform kinetic interpretations with a scheme based on the combination of a primary reference fuel scheme, an ozone submechanism, and a NOx submechanism. These computations were performed in agreement with the experimental results. And here is presented the initial delay for isooctane and 20 ppm of each species. The trends are well reproduced with ozone, which lead to the higher advance of the initial delay, and NO2 to the lower. From this result, we perform a reaction pathway analysis. So, as I said before, the fuel start to oxidize with O2 molecules and lead to the formation of an OH, which strongly improve the oxidation of the fuels and therefore lead to the occurrence of the combustions. In the case of ozone, this is the O atom coming from to the ozone breakdown, which directly lead to the formation of the OH radicals. In the case of NO have to react with the HO2 coming from to the normal oxidation of the fuels before producing the OH, which enable us to advance the combustion. And finally, in the case of NO2, there is a formation of an intermediate species, which is quite stable, and finally lead to the OH productions. Therefore, this graphic explains why ozone lead to the higher impact and NO2 to the lower. Know that the impact of each chemical species is well known. We can consider a seeding with both ozone and NO. Here, it presented the in-cylinder pressure and heat release rate trace for a seeding with both species. When we have only NO, we have an improvement of the combustion. This is the green curve. When we start to inject ozones, we have the occurrence of a short delay, and finally, continuing to increase the ozone concentration seeding into the engines, this leads to another promoting effect. To better observe the impact of the seeding with these two chemical species, we also plot the shift of the CA50 in reference to the case without any oxidizing species seeding. When we have, in all the cases, referencing to the case without any seeding, we have always an advance of the combustions. When we start to inject NO, we have an improvement of the combustions. And finally, when we start to increase the ozone concentration seeding into the intake of the engines, we have the occurrence of a delay up to a concentration of ozone, which is approximately the half of NO. And finally, we find a new trend, the exponential trends, due to ozone. So this means that there is probably a reaction between ozone and NO. To try to explain this, we chose to make computations with the constant volumes that I present you before, but unfortunately the results show that do not reproduce the trends observed on this graph. Finally, we measure the ozone concentration at the intake of the engines before the entrance of the fresh gases in the case of in a motoring case, and for two initial ozone concentrations, and by increasing the NO concentration. We observe that at the entrance of the engine, the ozone decreased linearly with a slope of 1. This means that there is reaction between the two species, which lead to the formation of NO2. As we have NO2 present into the initial mixture, this explains why we have always an advance of the combustion in all the cases, referencing to the case without any seeding, and that's it. Finally, we perform computations in two steps. A first step which considers the constant volume in front of the intake pipes and the combustions, and we reproduce with success the experimental results. So now I can consider a first application of the ozone generator. Instead of injecting pure oxygen into the ozone generator, I chose to inject a dry air. The objective of this part is to compare an air supply with an oxygen supply, and also to show that a dynamic control with an ozone generator is possible. Before to present you combustion results, I would like to present you the ozone production as a function of an oxygen supply and compare it with an air supply. We can observe that by increasing the ozone generator capacity, we can produce more ozone. So that's it. This ozone productions increase linearly. And in the case of air, we have more ozone produced than expected. In fact, in air, there is five less time oxygen compared to pure oxygen. But the ozone concentration is not five less time. Also, we can observe an impact of the combustions. An impact of the temperature, the intake temperature of the engines, which increase the ozone concentration. But I said before that, in fact, ozone must decompose earlier due to the temperature, due to its sensitivity to the temperature. These results are due to the use of a constant oxygen flow, which crosses the ozone generator, while for the engines, increasing the temperature results the flow of the main reduce the main flow, and therefore the dilution is lower. So now I'm going to present you the combustion result in the case of an air and an oxygen supply. So we can observe that by increasing the ozone generator capacity, we can advance strongly the combustion phasing of the maximum pressure location. In the case of air, as we produce more ozone, we can advance more than with an air supply. Also, we perform this experiment for 3 different intake temperatures, and as a function of the temperature, a minimum capacity is needed to tune in order to make combustion possible. This also shows that we can control the combustion phasing under lower temperatures than those necessary to initially autoionic isooctane. So we can also compare these results from the ozone generator, the ozone concentration injected. In fact, there is no difference between an air and an oxygen supply. And it was, we can ask us, are we, do we have nitrogen concentration at the intake of the engine? And we try to measure it with a Bay analysis, and we do not measure any trace of this chemical species. Also, this shows that with air, we can inject a maximum ozone concentration close to 40, and as we need higher ozone concentration to ignite the combustion at 100 Celsius degree, we have not enough ozone produced with air, and unfortunately, we cannot have results at this temperature. But finally, we can show that it is possible to control the combustion phasing over a wide range of temperature. Also, even if we have no NOx at the intake, it can be have NOx into the residuals of the combustion chamber. We measure the NOx at the exhaust of the engines, and this concentration do not exceed 5 ppm. 5 ppm, this is a first production of NOx due to the in-cylinder temperature, which was estimated close to 1,800 degrees. So the concentration measure is very low, and we can estimate the residual at 6%. So therefore, we can neglect the NOx and any interaction with the ozone into the combustion chamber. So finally, we finally perform a cycle-to-cycle analysis, as the ozone generator has been modified to enable a remote control of this device. We try to control cycle-to-cycle the engine. In this case, we chose to inject the ozone close to the intake pipe and to perform a control based on a feedback from the maximum pressure location. Here is presented the cycle-to-cycle measure for a decrease for an increase of the maximum pressure location, so an advance of the combustions, and a delay of the combustions. As you can see, the cycle-to-cycle take a few cycles, approximately 10 cycles, before obtaining the target. So this occur in 2 steps, which are identified on the engine. The first step is due to the time for the ozone to arrive into the combustion chamber. And the second step come from the ozone production into the ozone generator. The ozone generator has a big volume which have to cross before achieving the maximum ozone production on this point. So to conclude on primary reference fuel and therefore on these first objectives, we investigate 3 different oxidizing chemical species. We made computations to interpret the results. It was observed that reaction between these oxidizing chemical species have not to be neglected. Control with such an engine, with an ozone generator is possible. We also observe that there is a main importance of the intake temperature. Finally, a first application was considered, and we successfully proposed a dynamic control. Now I'm going to discuss the result obtained according to the second objective of my thesis work, which was to investigate the impact of ozone on different fuel classes. In this case, we only choose to perform the experiments with this configuration of the engine, that is to say, with a pure oxygen supply for the ozone generator and the nitrogen flow to have air, fuel, and ozone at the entrance of the engine. Before discussing the other fuel selected for this study, I just want to remind you the result obtained for primary reference fuel. We observe that we have a general effect, which is an improvement and an advance of the combustion phasing, and that ozone may control the combustion phasing by varying the concentration seeding into the engine. We also observe that due to its strong, this powerful oxidizing effect, we can decrease the ignition temperature of the fuel. And finally, we observe that the effect comes from the O atom, the O atom coming from the ozone decompositions, which lead to an early production of OH and therefore an early ignition of the fuel. So now I'm going to consider another fuels. We selected gaseous fuel. The motivation for selecting this fuel was due to the impact of the ozone on isooctane. We observed that we can strongly decrease the intake temperature of the engine, and therefore we ask us these questions: is it possible to use ozone and autoionic fuel, which are more difficult to autoionic than isooctane? The best examples are methane and hydrogens. Here is presenting the iso-CF50 for hydrogen and methane in the case of varying the intake temperature and the intake temperature and the intake pressure of the engines in this condition. We can observe that unfortunately pure methane does not autoionic in spite of tuning the maximum intake temperature and the intake pressure. But in the real case, methane is never used pure. It's always mixed with other fuels, such as in natural gas or with ethane. In the case of hydrogens, hydrogen autoionic more easily than expected. In fact, it has run and mon very high compared to isooctane, but due to its high reactivity, it may autoionic more easily than isooctane. So, based on these results, we try to use ozone first to we investigate its impact on hydrogen. We can observe here the trends for the CA50, which is similar to that already observed for primary reference fuel. We also try to perform the same experiments in the case of methane, but unfortunately, even if by using ozone, we can't auto-ignite pure methane. So this means that fuel is of main importance for considering the use of ozone. So I said before that methane can be mixed with other fuel. So for example, ethane, which is composed of 80% of methane and 20% of hydrogen. So we choose this fuel and try to injected ozones with condition near to the maximum for the engines. And we also saw that we have the same trends than those already observed. We also try to mix, to change the ratio of the fuels and continuing to control the combustions with ozone. And this is also possible with a minimum ozone concentration, but a minimum ozone concentration is needed. As these results were performed to the maximum condition of the engines, we also observe in this case the exhaust NOx. In order to consider a possible reaction of NOx with ozone during the induction stroke. As the intake conditions are very high, we have high level of NOx. We have high concentration of NOx produced. And therefore, considering the part of residuals, we can have a maximum of NOx into during the entrance of the fresh gas of 72 ppm, and therefore, as we perform, we vary the ozone concentration up to 80 ppm of ozone. It could be possible that there is interaction between these two species in this case. So, in fact, the intake pressure was very high compared to the exhaust pressure, and therefore there is a swap of the residuals, and therefore we can consider that there is no interaction between ozone and NOx into this case. But in other cases, this has to be considered. Finally, in the case of gaseous fuel, we also interpret the results from computations with another scheme based on hydrogen, CO, and fuels from C1 to C4 with the ozone submechanism. And we observe that in the case of ozone, we have the similar results than those observed from primary reference fuel. That is to say, an indirect impact of ozone and an early OH productions, which strongly advance the combustion, the ignition of the combustion. So, to conclude on gaseous fuels, we observe similar effects than for primary reference fuels. We also can consider that the fuel structure is of a main importance, as methane does not ignite with ozone, and hydrogen the combustion of hydrogen was strongly advanced. So it is also possible to perform a control of the combustions by changing the ratio of each fuel. And additionally to the result here presented, other experiments were performed with methane propane as fuels, and it was observed that it is possible to use ozone and decreasing the intake pressure and intake temperature of the engine and controlling the HCI combustion. Now, I'm going to consider the last fuel selecting for this thesis work, which was alcohol fuels. The main reason for choosing these fuels, it was alcohol fuel include an oxygen atom into their compositions, and therefore we ask us if the fuel structure and the presence of the oxygen atom will modify the impact of the ozone. So, as previously presented, here I presented the CA50 for a location at the top dense center for 3 different alcohol fuels: methanol, ethanol, and butanol. We can observe that butanol autoignite the most easily due to its Ron and Mon and therefore octane number index. And ethanol autoignite the least, also due to its octane number. We also observe that there is a convergence of these trends at high temperature, which is due to the sensitivity of this fuel. So, as there is a convergence of these fuels, we choose to perform our investigation of ozone with these fuels based on the same intake conditions. That is to say, 1 bar and 170 Celsius degree, which is the minimum temperature needed for autoignite, the most difficult to autoignite, that is to say, ethanol. Here is presented the impact of the ozone on the shift of the CA50. We can observe that we have also similar trends than those already performed. Compared to the other fuel previously presented, it is necessary to inject higher ozone concentration to achieve, to reach the same effect on the shift of the CA50. Also, there is a difference between these 3 fuels. Butanol has the ozone has the most impact on butanol combustions, and the least impact on methanol combustion. So, this means that, in fact, the fuel structure and therefore the number of carbon atoms into the fuel structure has an impact on the ozone ozone effect. So, to interpret the results and the effect of the ozone on combustion of alcohols, we perform kinetic computations, and here is presented the initial delay for the 3 fuel represented. As you can see, the trends are well reproduced, with methanol and ozone which are close from each one, and the initial delay for butanol is more advanced than for the 2 other ones. Finally, we also observe an higher effect for butanol and the lower effect for methanol for the ozone impact. From these results, we can observe the kinetic pathway, the main kinetic pathway, and here again, compared to primary reference fuels and to gaseous fuels, we have the same impact from the ozone, which is an indirect impact coming from to the O atom, which is produced with the ozone decompositions and lead to an earlier OH production. So, to conclude on alcohol fuels, we observe that ozone also improves and advances the combustion of alcohol, like in all the other fuels selected previously. It seems that there is a chemical impact due to the structure of the fuels. Therefore, fuel is of main importance for considering the ozone impact. And we also observe that, in fact, ozone leads to the same effect than for primary reference fuels and gaseous fuels. So, to conclude on my thesis work, first, about the first objective of my work, which was to evaluate the potential of using an ozone generator and trying to control the HCI combustions. We investigate 3 oxidizing chemical species and observe that the higher impact is due to ozone and the lower is due to nitrogen dioxide. We also observe that we have to consider interaction between ozone and nitrogen oxide. And finally, a control of the HCI combustion is possible by using an ozone generator. Finally, we try to make a first application which was successfully implemented. About the second objective of this thesis work, which was to investigate the impact of ozone on different fuel classes, we observe that the general effect of ozone is always to improve and advance the combustion phasings, and there is an indirect effect of this oxidizing chemical species due to the formation of an oxygen atom. Finally, we also observe that the fuel structure is of main importance. So, this project was quite innovative, and therefore we can make a lot of prospects. The first will be to explore other operating range. We focus on only one operating conditions. Then, if we want to explore other operating range, probably it will be necessary to use diffusion or EGR. Therefore, interaction between EGR components and ozone must be considered. Also, I mainly perform computation with a constant volume model, and therefore it will be necessary to extend these computations with CFD1. Finally, maybe it could be help in order to well know the impact of the ozone during the compression stroke of the engine by using an optical access engines. Also, it seems that there is a lot of kinetic interactions at the entrance of the engine, and therefore it will be maybe needed to investigate further this chemical interaction. Finally, for future applications, we use an ozone generator, which is a commercial device during this work. And now we can consider optimization or the design of another one which will be more suitable for an engine applications. Finally, I mainly investigate HCI combustions, but for future application, we have also to consider other advanced combustion modes. And finally, we focus on 3 different fuel classes, but maybe it will be better to investigate other fuels. So I would like to acknowledge ERC for funding this work, and I thank you to all of you to be here today for evaluating this work, and I let the place to your question.
Thank you, Jean-Baptiste. So now we will have the committee asking you some questions. So we start with the 2 external reviewers. First, we'll start with
Thank you, Mr. President. Thank you very much, Jean-Baptiste, for this very nice work. Let me start to congratulate you for the nice presentation that you made today, and for your report, which is concise and very instructing, and shows the very large amount of work that you have performed during your thesis. It's a work performed in a very sound scientific way, as I've written in my report. When you started from not a simple problem, but the simplest that you could find, and then you added complexity towards the end in order to understand step by step the density of your work. I appreciated that a lot. Also, one thing that I have noticed and I have written on my report is the amount of publications that you have made. 6 publications. It's quite impressive for
Thank you.
work. It's very, very nice. And also, one thing that I would like to highlight is the process of using experiments and simulation at the same time in order to provide explanations for your work. That was highly appreciated. And I think today, with the capacity that we have of supercomputing and using very large mechanisms, kinetic mechanisms to perform computations, it's very nice that you have used both. It's almost mandatory today to do that kind of work, and you've done it and you showed it in a very nice way. Before asking you questions, I also have a few comments of things that I think you could have also improved on your work. One of the things is that, given the amount of work that you have made, sometimes in your manuscript, I was missing some information regarding, for example, validation of kinetic schemes and things like that. I think you that information is present on some of your publications and other publications, but sometimes a figure here and there to complement on the information would have been nice. Also, with the amount of publications that you've made, of course, they are all available online, but it would have been nice to send them along with your report, because that would emphasize the amount of work that you have done. But it's just of course,
yes.
a general comment. And the last thing, the last comment that I'd like to make is that I think sometimes your work is mainly experimental work, as you have done a lot of experimental work.
Yes,
and
of course.
Sometimes I think you were a little shy of presenting, of highlighting the modeling work that you have also performed. So sometimes in the report you put things like, we think that this might go like this or like that, and then you show us the computations, you show us the results, and you show, okay, this happens because of this and because of that. I think mixing both in the presentation and in the text would have been better, in order to say, okay, it's not an assumption that I've made and I'm going to test it later. I make an assumption, I test it, I explain why this happens with all the tools that I have, both experimental and modeling tools. That would have been more easy to read your report in that way. But of course, this doesn't remove any quality from your work. And these are just comments in order to maybe improve it.
I will try to consider for improving my manuscript.
I have a few questions. Let me start just with a couple of questions regarding some of the things that you said during your presentation before making more general questions, which I didn't quite capture. At the beginning, you said that ozone changes the fuel structure. Maybe I didn't get it right, but what do you mean by ozone changing the fuel structure?
In fact, it was some works performed by Alexander Chambord. In fact, it injects ozone in a tank which contains fuels and let it oxidize the fuel progressively during a very long time, and it observes that with this process, the fuel structure is modified. So, for example, if I consider basic fuels with carbon and hydrogen atom, the O atom coming from ozone can fix and create a new fuels. So it performs its work with different kind of fuels. I can't describe more like this.
What range of temperatures and the residence times are you talking about?
If I remember, it's like last publications. The process is about 4 hours, but it let it 1 night.
Okay, so it's really a very long time at low temperatures.
Yes, okay. It's very long time.
Okay, and just another general question regarding your presentation. This, I don't think I have read it on the manuscript, but maybe I'm wrong. What you are talking about using an external device which needs energy to be operated. That energy is coming from somewhere.
Of course.
Related to one of the objectives, of course, of using different types of combustion systems is to improve the energy efficiency of the system. Do you make an analysis of the amount of energy that you have to use to generate the ozone and compare it to the energy that you may gain from a better engine efficiency? Or
I don't know which kind of parameter we can modify to have a device less with a lower power consumptions, but we measure the power consumption of the device uses, and it is close to at the maximum of the capacity, close to 100 watts. So it's still very important, and there is a lot of optimization, improvement to made before integrating, considering a very real integration into a passenger car. That I can say the best objective will be to have an ozone generator which can consume a similar energy like maybe a plug, so something like that. It will be the best one.
It's just to highlight the fact that when you use something to improve combustion efficiency, which draws energy, it's important to know how much energy
Yes.
is being.
Yes, of course.
being
So it's very important compared to the work produced at the end, but obviously a lot of improvement have to be.
I have a few questions about general questions about your work. Of course, you had to use during your work, especially because you were making modeling afterwards, you had to choose surrogate fuels. But as you've shown, at the end, one of your conclusions is that ozone is the effect of ozone is very dependent on the fuel that you are using, because the chemistry is
Yes, of course.
different. So for you, what is why only choosing PRFs, mixtures, well, either azoctane or heptane? And for you, what is a good surrogate to use in this kind of work regarding the effect of ozone, which is quite dependent on the fuel structure?
In fact, before considering the combustion of TRF or similar surrogate of gasoline, I think that first it will be to consider the ozone impact on toluene, only to observe if there is the same kinetic pathway on the effect of the ozone. Then after we could consider toluene reference fuels. So for me, which fuels would be better? In fact, I can base my results on this graph. You can observe that isooctane have a combustion. This is an array of the combustion. This is CA50, so the I limit correspond to the Crank angle degree, the CA50 at 1 Crank angle degree, and the lower to 5 Crank angle degree. And we observe that in the case of isooctane, we can strongly decrease the intake temperature tune on the engine by keeping, I have the results, so it's in the central place. So without ozone, this is the red array. Yes, thank you. So here is isooctane with 0 ppm injected, and we can translate this array towards lower intake temperature. So for real consideration of the fuel for an engine application, we can't imagine that we have such a temperature of 200 degrees. And we have also the impact of ozone. If there is no ozone, there is no combustion. So we can imagine combustion. So I imagine a combustion of controlled by ozone, with a minimum ozone injected to make possible the combustion. So I take back on this graph. I could be consider PRF 95. So probably it will be in this area, into this graph, and combustions will be possible and with lower intake temperature and high intake pressure. And I could be chosen to make my experiments at 1 bar or lower. And if gasoline, I can call it gasoline, take place in this part with ozone, it could be even this is possible to modify the area of combustion into such a zone and entirely control a fuel like gasoline, surrogate fuel.
So if I understand your answer, what you're saying is that you should use fuels that can ignite at lower temperatures than isooctane.
By using ozone, decreasing the ignition by using ozone. So the control will be entirely based on ozone.
Okay. Well, a question about the choice that you've made on your modeling work using the constant volume setup. Given the importance of ozone decomposition, even at low temperatures, and the effect of ozone with the fuel, even at lower temperatures, why did you choose the constant volume setup rather than, for example, an ICD setup, which is also available in Sentin, that could have given you the history of the oxidizing paths during the compression stroke, which might be important given the low engine velocity that you have used?
In fact, the main objective was to investigate the kinetic impact, and we chose to perform the computation at for a time. And with this modeling, we can avoid the presence of aerodynamics, so it does not change a lot the combustion since we are homogeneous, but it can have temperature stratification into the combustion chamber. So this was to avoid this, and also to avoid heat losses that it can have. So the main reason was.
You can have an IC module in Sentin with adiabatic conditions.
Yes, but after what I have available, also it was one area model, and for make computation and that the result be in agreement with the engine experiments. I think it's better to use CFD, some more complex modeling. So I only stay on a base. And finally, we perform such a fuel. So I'm not modeling CFD, but with a collaboration with Francesco Contino here. We try to perform such modeling, and the results are in good agreement with that we done during the experiment. So I can't explain you the modeling because I consider myself more than an experimenter than a modeler.
Just to continue on the modeling side, you present on your report on table 4 the different mechanisms that you have used. What led you to the choice of these mechanisms? Because the literature is quite abundant, and there are a lot of mechanisms, different mechanisms in the literature. Why did you choose these specific ones?
For fuels?
For the surrogate fuels that you used, and also you mentioned that your methane mechanism was improved
in
I
the
want to know where did you update it and why? So first question is why the choice of these surrogates? The second question is
okay.
which modifications have you made on the method mechanism?
For the choice, it's only bibliography part. For primary reference fuels, the modeling of from Kuran et al. It's for myself the better one because it was validated on a wide range of experimental results. For the second one, where we consider gaseous gaseous fuel. At the beginning, I start with Grimmage modeling, but unfortunately, I can't modeling. The result does not satisfy what I observe with ozone, and therefore I chose to select another model, which was based for Quran. The result was validated on a wide range of experiments, and for alcohols, it was quite complex. In the beginning, I observed lot of kinetic scheme, but I would like one which can help me to modeling all the alcohol that I select. It was the younger the younger models that I find which helped me to modeling butanol in particular. After about the improvement of modeling, I think that this is still a question that I have to discuss with my advisors. I think that we have to perform more modeling, maybe by using CFD.
My question was not on future work, was on the fact that you say that you have updated the methane mechanism, and I just wanted to know where you have touched the. When you present on table 4 in your report, the methane mechanism, you say okay, the Wang, I think it's the Wang mechanism, has been updated. I just wanted a few details on what you have updated.
What? Okay, sorry, I don't well understand your question. So it was in table 4. You sent me in table 4.
It's on page 104. You mentioned that.
So you think that I made some update?
You mentioned here, in the beginning of page 105, the scheme is based on several mechanisms and was updated. Just wanted to have a few details on what you...
Yes, no, in fact, no, I think this is a mistake from myself because I do not made any modifying on the base kinetic scheme. No, the update, I don't find that. I think that the update that I consider is maybe the because I build a new a new kinetic scheme just by adding the ozone sub-mechanism or nitrogen oxide sub-mechanism. So yes, I think this is a mistake from me.
So to finish with the kinetic part, you used and precisely used an ozone mechanism which, if I understood well, was developed for flames. This means high temperature combustion, whereas you are using it to study auto ignition. So what do you think is the validity of this mechanism in low temperature chemistry as the one you are using? How do you justify the use of a mechanism developed for flames in the low temperature chemistry regime?
Yes, I will see your questions, and this is a very interesting question. I asked myself during the thesis. In fact, ozone is very, very, very sensitive to the temperature, and up to temperature such as 600 Kelvin, it decomposes or it consumes immediately. So it is not needed to go further on the temperature to consider it. I don't know what more details that I can give you. So this is my point of view. Maybe we have to consider this some mechanism on other experimental device, more simple than an engine experimental setup, and but the constant for determining the rate constants are already fixed by a lot of work already performed. So I don't think that we have to change a lot.
Okay, I will stop bothering with kinetics, which of course is not the core of your work, but it's an important part of your work. Let me just finish my questioning with a general question, a perspective question of your work. You mentioned at the beginning of your report that when you study diesel engines, HCI engines, well, all kind of combustion engines that are related to auto ignition, there is a sort of HCI index that might be built to better represent the general combustion, the general auto ignition process, which can be used rather than octane or cetane. A lot of people have worked on this sort of HCI index, which might be defined in a lot of ways, but when you study the influence of species like ozone, NO, and so on, do you have an idea of what, this is a completely perspective question, okay? Do you have an idea of how to define such an index for HCI combustion based on reactive species that you can add to your combustion system in order to improve it?
This is quite a difficult question. There is several work already made on this topic, and this is a very hot topic. So what you mean is that we could use oxidizing chemical species in order to determine.
For example, some people just they say that an HCI index can be defined, for example, as a function of a linear function or a nonlinear function of some of the components of the fuel, some important components of the fuel.
Yes.
I was just wondering if you had imagined how such an index could be defined for.
From my own experiments.
Where you use.
In fact, I will take the based on this result. So this is the really first experiment that I done during my thesis work. We could use something like that based on a unique rotation speed and equivalence ratio, and attribute fuels which burn in this area as with an index of 0. So that's it. And for other fuels which based on this, like 100. So this is a first and a second to attribute, and all the fuels that burn into this array, depending on the mix of isooctane and n-heptane, we could attribute an auto-ignition index. After that, what we can propose for fuels, we can observe in this that there is a sensitivity. Sometimes, like hydrogen auto-ignite early than isooctane. So I think that we could use this base to define an auto-ignition index, and that's it. That's it. So we.
Thank you very much, Jean-Baptiste, for your
Okay.
nice work. And thank you, Mr. President.
Thank you. So now we will ask the list to comment.
Merci, Monsieur le Président. Thank you, Mr. Azurier, for your work and your presentation, which were very, very nice, as it has been already said. It's quite an original work, as the radical adding to the mixture as a way of controlling the HCC seems to be a promising way of increasing certain parameters on the engine. So thank you first for the work, for interesting to this kind of subject, and thank you for the quality of the not only of the manuscript but also of the analysis that has been made. I will say also that as it represents a lot of work, some extra description of the experimental devices, of the analyzers, of the all kinds of things could be welcomed. But you end writing a very big book, so in the middle, I will not tell you that it will be better to put something or not, but some details may be interesting to be added. I have some questions on different things. I'll try to be not too long, but I have trains and cars to take. But I will start by the same question about the energy efficiency, which you have already answered. But I was also questioning myself about the efficiency of conversion of your ozonizer, say? If you enter 100 moles of oxygen, how many ozone they go out?
You go out to the engine?
Out of the ozonizer.
How much?
In terms of volume or mass?
In volume, the maximum quantified was 2% of ozone dilute in oxygen. So.
Sorry, I'm asking how much ozone you have out of the oxygen in the ozonizer.
Yes, out of this part.
Yes.
Yeah. In fact, we can produce the ozone generator. So the commercial device that I use can produce up to 20,000 ppm.
Okay, and the efficiency of conversion, you say, is 2%?
Yes.
Okay.
Yes. So yes, that's it.
Good to know. Because I mean,
With the maximum capacity.
Okay, because if you use 100 watts to produce 2% of ozone, we still have some.
But after it also depends, because we can observe that we need only a few ppm to strongly improve the combustion.
Sure. There is hope. There is still some hope. And I was wondering how to be quick. How confident are you on the ppms at the intake? You have an ozone analyzer at the intake that allows you to measure the concentration, or is it the result of the calculations and the flow rate adjustment?
No, this is an ozone measurement, and we measure directly the ozone concentration seeding at the intake of the engine.
And this analyzer has what kind of
This is a commercial ozone analyzer. We just need to make a sample of the mixture at the entrance of the engine, and it is sent directly into the input of the ozone generator, and then the measure is based on a measure of the light intensity from an UV lamp.
That's part of the question, very basic questions that arise very often. But in some cases, the concentration of ozone is quite low and has real influence on combustion. The sensibility and the error made on measurements could be interesting just to mention. There's no doubt that you have calibrated measurements and everything, but it's always good to say a word about that.
Okay.
On a completely other subject, is this HECI? I mean, you have a premixed ratio.
Yes.
In an engine, and you compress, and
it's init. Yeah.
I'm surprised that you never mentioned any knock problems.
In fact, we can. I could be determine ringing index to determine the such a knock. I measure it. I present the results on the figure. Which one? Yes, it's figure 81, page 151. So this is not the ringing index, but the gradient of the maximum pressure rise rate, and if we go further than 10 bar per Planck angle degree, at this point we start to have a very important noise from the engine. So lower than this limit, we can consider that we have not knocking.
And when you suspected that when you compress mixture, you have some knocking problems, and you present experiments with zero concentration of ozone, how is that you have so few cases of intense knocking or very fast auto-ignition? What is the fuel air ratio, for example? I'm sure it is written somewhere, but I don't remember.
The fuel air ratio is 0.3.
0.3.
Yes.
Okay.
Always the same equivalence ratio.
Okay, and what is maintained constant for all fuels is the equivalence ratio?
Yes.
The output power is the same, or you maintain the amount of fuel injected? What is constant for this?
No, we have with the same equivalence ratio, but not with the same energy injected. It depends of the energy of each fuel.
Okay. And as I have said in my report, one of the questions is what happens when you go into other, let's say more, not more real, but closer to high recharge or things like that in real engines. How will it work?
I don't know because we do not made it up to now, so this have to be done. If I increase the load, so we can go, we can advance the combustion phasing, and therefore less ozone will be needed, and the inverse if we decrease the load. And with the engine speed, if we increase the engine speed, we can delay the kinetic time of the reaction. Therefore, the combustion is delayed, and we probably have to increase more the ozone concentration to obtain the occurrence of the combustion.
We probably made it, but the comparison without of the engine functioning with and without the ozone enrichment, I'm considering especially the HCI functioning. What can you say about that? If one can use an engine at the ratios, at the compression ratios, FE ratios and compression ratios you have used in an HCI mode without ozone.
Hmm?
But I was wondering if you have particularly studied this engine with and without ozone for all fuels, or not. I know that the study.
I don't well know your
Yes,
what you mentioned.
That's not always easy. You tested all PRF fuels in the engine?
Yes. No, not all the not all the PRF. Only 6. That's one I present.
Yes, but from PRF 0 to what?
280 by a step of 20.
And is there a figure where you have a comparison of 0 and ozone regarding HCI functioning in this engine for all the fuels?
For all the fuels. Yes, okay. In fact, I only made it for primary reference fuels and for alcohols, but the main problem is that the initial conditions for all the fuels are not the same. So we can made a comparison of all the fuels directly like that, but we have also to consider that the intake conditions are different. So it is not obvious to say that ozone will have more impact on a fuel and less impact on another. So maybe we could be perform it with kinetic mechanism.
I was talking about figure of your transparency 18. If you can
So
18.
18.
So we see that for PRF 100, of course, you still manage to have an engine working at 0 ppm of ozone.
Yes, the intake conditions was fixed for isooctane for starting with the auto ignition of this fuel with a combustion phasing of the CA50 at 6, and we also consider this for all the other primary reference fuel. But for isooctane, the intake conditions that we have to tune are a high intake temperature, close to 200 Celsius degree. for all the other primary reference fuels, we are at the ambient temperature. So we can easily compare all the primary reference fuels except isooctane. So that was I said on this result that the high sensitivity to the ozone for isooctane is due to the intake temperature tunes, which lead to an earlier ozone decomposition.
So it's interesting, particularly that for PRF0, for example, you don't manage to have a good combustion without ozone.
I chose to start from these experimental points due to the strong impact of the ozone, in fact.
Could you say why you don't have PRF0 points for lower concentration of ozone, lower than 5?
I don't well understand your question.
Figure here.
Yes.
PRF0 points.
Yes.
Stop at 5 ppm of ozone. Is that true?
Oh, no. I go up to 50. Comment?
Est-ce qu'il y a des points entre 5 et 0?
Ah, okay. Yes, I don't well see here. No, normally there is, but maybe we don't well see it due to an overlap of the other combustion point.
So
But
are there or there are not points of PRF0 at 0 ppm of ozone?
There is a point at 0, 1, 2, 3, 4, 5.
Okay. So you can make this engine work as an HCCI engine without ozone?
Yes.
Okay.
Yes, of course, I can. But I have to tune minimum intake conditions.
Yeah. Okay. You talked in Transparency 28 about simulation problems.
20. This one?
Yeah. I didn't understand.
Yes, in fact, we can observe that we have the occurrence of a delay compared to the initial NOx injection, and when the ozone concentration is approximately the half of NO, we found another trend which is characteristic to the ozone impact. In fact, we made computations of this result, like I done during all my experiments work, by only considering the constant volume. And the results show that, in fact, the emission delay, it is the figure, so it is figure C70, page 140. So you can observe on this figure that, in fact, we have the effect of NO and the effect of ozone. And when both are considered, we have a combination of these two oxidizing chemical species, which strongly advance the combustion, the ignition delay, but it is not consider that we have a combination of the two, so the ignition delay of each one are added to the other one. And in fact, there is NO and ozone reactions which lead to the formation of NO2, and this, in the kinetic pathway of this result, figure 70, are not considered. But with the experiments, we observe that the ozone decrease as a function of the nitric oxide nitric oxide concentration injected, and finally we chose to perform a two-step computations with the scheme on figure 72 on the next page to try to, in fact, modeling the ozone and NO reactions that we can have into the intake of the engine before the entrance of the fresh gases, and then a second step which corresponds to what can happen into the combustion chamber, and that result with a two-step hatch purge gives the result and help us to explain the trends observed with this delay, which are in fact entirely due to this reaction.
Well, we still have to discuss. One last question, more general also, is that when I was young, I learned that HECI was good because we had a good compromise between particles, NOxes, and fuel and engine efficiency. When I read your manuscript, I was very worried about NOxes at the exhaust. I had the impression that the enrichment with ozone traduced in an increase of NOxes at the exhaust, but this is not true, or is it?
In fact, NOx depends on the temperature and equivalence ratio. So if I take this diagram, in fact, as soon as I reach high temperature, I can start to produce low ppm of ozone. So the temperatures that I give you during my presentation is an average. So maybe there is higher temperature inside the combustions that are responsible of very low NOx formation. In the case of isooctane, it was very low. But in the case of gaseous fuels, the intake conditions was very high, and with the compression and the combustion, we can reach such a temperature, and we are totally in this point. So that explains that the presence of NOx into the HECI combustion. The better for HECI will be to be and stay in this area, but in fact sometimes it could be extend in this area.
Thank you very much. So now we will ask Professor Didier if he has some comments and questions.
Thank you, Mr. President. Thank you very much for your thesis. I truly enjoyed reading it, and it brought back a memory of a now ancient movie called Chariots of Fire. And this was a story of runners, people who would run a foot race. And one such runner thought that he was pretty good. So he goes to what he considers the best coach and asks for help. And the best coach, I think, was Dustin Hoffman, who, interestingly, is smoking a cigar for a runner. And he says, I cannot put in what God left out.
Hmm?
So, when I read your thesis, I think, there's something here. God did put something in. So now I give you the other quote, and that is, to whom much is given, much is expected. So you have a gift, and we will be watching you, and we expect great things. So I can share the comments that my other colleagues have said. They're all correct. I agree with them. And I've so much enjoyed your thesis that I will talk to you later because I have ink on every page. Ready. Because it is so good that I'm able to say you can make it better. You can tweak it here and you can tweak it there. And these are, we say, tweaks. They're not corrections. It's perfectly fine the way it is. It can be better. Now, just for your benefit and the benefit of my colleagues, and in particular the benefit of people in the audience, that they think that these old professors don't read it, I have two questions. Serious questions. As proof that I read your thesis, okay? Here we have on page 66.
666.
Yeah, I'll read it to you. Now, you might have to look it up yourself, but I will read it to you. It says something about delaying the intake valve closure. Okay? So the piston is lower, and therefore the effective compression ratio is reduced. True. Next sentence. This results in lower in-cylinder temperatures, which reduce the ignition delay.
Okay.
I think you need the word increase the ignition delay.
So,
Again, page 66.
so
You say
66.
you lower the temperature and you reduce the ignition delay.
So this results into lower incident, which reduce after the effective is lower, and therefore the effect reduces. This results into lower. Yeah.
We'll vote on it. We'll do a democratic vote, okay?
No, it's
Okay, we'll talk about it
so
later.
no, we have a lower in-cylinder temperature, which increase the initial. Yeah. Okay.
Okay. So, prove that I'm reading your paper, okay? Okay, now on page 173, you say that we're going to decrease the intake pressure.
Which page?
173.
173.
And it would be sentence down to the top. It's sentence about number 6.
17.
We're going to decrease the intake pressure, and this, okay, due to the lower, as a consequence, you say that we're going to have lower in-cylinder temperatures.
So
So I claim merely decreasing the pressure will not change the temperature in cylinder.
where is it?
Okay, again, it's page 173.
173. Okay.
And it's sentence down from the top. 1, 2, 3, 4, 5, 6. 6
Okay.
sentences. This is due to the lower in-cylinder temperatures reached inside of the combustion chamber.
And so it is also needed to see the minimum and to knock the fuel. This value must increase exponentially with the decrease of the intake pressure to the low. Yes.
Okay.
I don't know. I think that it's useless.
Okay. So just proof that people do read your work, and in fact, you will get disappointed in your life, as I have, that, dang it, you seem like you put a lot of work into these manuscripts, and then you feel bad that not very many people read them. But the good news is, the people who do read them are truly interested in what you write. And for that, we are grateful. And so it is for those people that we are writing for. Most people will not read our papers, okay? Another comment is, in your slides, you show us a picture of ozone?
Picture of ozone. On which slide?
Yeah, you'll see it. One of these has it. I could tell you. There.
Okay.
Well, that's what you must have pulled out of some computer program. that's water, you know, or something. But ozone is a triangle.
This is the view. Ozone is 3 atom oxygen. Oxygen is red, so there are 3.
Just to tell you the truth, I'd be happier with O3 than that, which it looks like propane or something. Okay. You know, one other question kind of comes up. Thank you for referencing that great paper from the year 2003, of which I'm last author. In that paper, we show the chemical constituents as a function of crank angle degree.
Yes.
So we are steadily compressing the gas, and you can see some species appear and other species disappear. So I ask you this question, and that is, if I have a motored engine and I put in ozone, is there any ozone in the exhaust?
In fact, into the engine, the compressions may reach temperature such as 600 Kelvin or more, with only a motoring, considering only a motoring, and this such a temperature entirely decompose the ozone and recompose into oxygen molecules or react with other species. So there is no more ozone at the exhaust.
Yeah. So, in effect, you're telling me that probably by 20 degrees before top dead center, all ozone is gone. Yeah.
Yes.
So, let me nearly finish by going to where you were. You showed the it was your slide 29. So, congratulations, you're in combustion, and combustion brings together people who have a strong background in chemical kinetics, people who must understand fluid mechanics, people who have to understand computers, and a world to their own, and then, of course, you, an expert doing experiments which involved much iron, much metal, optics, ultraviolet light, ozone generators, many, many, many things come together. So I just tell you something that I sense missing in your thesis. In my class in combustion, I would ask my students, how many times must ozone hit NO to make that reaction go? It's a tough question, okay, and we'd have to look at the chemical kinetics, but I'm going to hazard a guess almost every time. So that's why I think you see what happens on the intake to your
Yes.
work. As I said, I'm eager to show you all my red ink, and I warn you that it's in great appreciation that I have made so many comments. I've enjoyed being educated by your thesis. Thank you. Thank you, Mr. President.
Thank you very much.
Thank you.
Now it's your time, Martin. I imagine that you have still some fresh questions.
If I have. Okay, thank you very much for this interesting and novel and fundamental research. I think it's important. I have quite many comments and so on, but we will not dive into all of them. So do you want the good news first or the bad ones? We can pass it through.
I don't know. It's up to you.
So on page 44, you claim that, actually you start before that with a very good review, I think, of a good start of your thesis here. But then you claim that the air-fuel mixture, which must be as homogeneous as possible in an HCCI engine. Why?
This is theory. The theory, we have to have a fully homogeneous air-fuel mixture. But after, what we have to consider that it depends on the approach for injecting the fuel. If, for example, I switch to an early direct injection inside the cylinder, for example, as I inject the fuel as soon as the intake pipe open, I can use the aerodynamics to mix fuels and air, but unfortunately I'm not sure that it is entirely homogeneous. I think that it is better to consider that there is stratification. So the fully homogeneous is not really true.
Can it also be that the fully homogeneous conditions is what is creating the problem for you, and that's why you need ozone to change the operating conditions? So I would be a bit careful with such an absolute statement. If we go to page 51, you have table 1 there, and on compression ignition engines, last in the table, you claim that they have higher hydrocarbon CO emissions. And this is simply just wrong, so you can remove that. And when it comes to spark-ignited engines, today we see problems with particulates. So you could add that as well.
In fact, in this table, we just do not consider the use of post-treatment system.
Sorry.
On this table, I only consider that pollutants that we can produce, but I don't not consider the post-treatment system.
But with compression ignition engines, you have very little hydrocarbons and CO produced from the combustion system. That's the benefit with that system. On page 64, you claim it is impossible to change the shape of the piston of an engine. I understand that you mean during operation.
No, no, I don't claim this, and it may have.
Research, we can pull them out and change them a little bit and put them back in again and do some research. We come to table 3 on page 83, and there's no references for the table. I think that would be good to have. And I assume that you mean the stoichiometric air-fuel ratio.
So, what did you say?
So it's on page 82, and it's table 3.
Yes, with the property of the fuels.
And in this table, you also claim that the MON value for hydrogen is above 130. I think this is a typo, but because you didn't have it in the presentation, you only say that RON has above 130. And this is the value we commonly see for RON, but we seldom find values for MON, for hydrogen. But there are some people that suggest that MON is very, very low for hydrogen. So it's a very strange fuel.
Yes, of course.
And very high, low MON. And that would explain why you later on have this behavior with the hydrogen experiments you did.
Okay.
I couldn't find the reference quick enough.
Yes, please.
For this. There was another thing. On page 95, I can see that you have been using for your modeling a cylinder wall temperature of 95 degrees, corresponding to the temperature of the coolant.
Can you explain why you selected this one?
I don't have a real justification about the choice of this temperature, but this is a parameter that I tune in the beginning, and I keep it always at this temperature. After maybe.
So it can be something else than 95 degrees. You tune this parameter, so you change it. Okay, so what would you otherwise say would be a more reasonable temperature for the in-cylinder wall surface? Do you have an idea? Or?
Sorry, could you repeat?
Yes, so what would you believe is a suitable or relevant temperature on the in-cylinder surface?
Something higher than the coolant temperature, so this is obvious. After I don't know, because it changed during the compression, but something like 100 Celsius degree seems reasonable, I think.
It would be higher,
On average.
Like you are discussing, I mean, it changes obviously with operating conditions, and you've been running very low. So I think 130 degrees at least, but it depends on where else in the cylinder we have this temperature. Okay, something more fundamental. How do you define a knot in your work? Because this is a limiting factor for your parameter suites.
In fact, I don't really define knock, and I don't really know how to define knock for HCI engine. So I will know knock for spark ignition engine, and we can extend like HCI engine is an overall auto ignition, like a big knock in volume.
But somehow, if you look at figure 50, I think I had it in the presentation also. That is the work on the PRFs.
Figure.
I think you could split up this figure so everyone can see. That one. Okay. So the upper limit here, that is, you have placed the limit here, and you call it, this is the knock limit.
This one?
Yeah.
No, it's not the, I don't not put a knock limit. I select maximum CFT at 1 conjugal degree, but the knock is still upper.
So let me see here. So what was the limit you put here? I didn't really understand that. Can you repeat that?
Could you repeat your question, please?
Yeah, but you have the limits of the operating ranges you have here.
Which limits?
You have a misfire limit on the lower side.
Yes.
And then you put. Okay. So this is the crank angle degree.
Yes. This is the upper and lower limit are crank angle degree.
Okay. Thank you. So. I understand it. Because later on in your work you claim that you should stay below 10 bar per crank angle degree in peak pressure rise rate.
Hmm?
Because
you could damage the engine, but later on you run with 20. So clearly it can take more, the engine itself.
Okay.
Another thing I was thinking of is that you are using the inlet temperature consistently in your experiments. Do you think this is a general parameter that we can easily translate to other engines? It's a bit leading question, so.
For the pressure, I think that there is a good stability of the pressure. For the temperature, we always wait a good stability for the 100 cycled recording of the temperature.
But if you would repeat your experiments on another engine, would you have the same behavior with the same inlet temperatures?
Probably.
Let's say that you tested on, I think you had 16 compression ratio on this engine and some specific load timings. And then you go for heavy duty.
If I take the same engine with the same piston, all the conditions identical, probably I could obtain the same results, but I'm not sure.
So could you maybe come up with a more general parameter for temperature, because temperature is so relevant here? Do you have an idea of that? Instead of inlet temperature, can we use another temperature in these experiments to present the results?
What do you mean? That is to change the temperature?
No, it's more on
the way you present the results.
Precisely how we present the results and in a more generic way. Because this, if you use the inlet temperature, this is very specific for this particular engine. But can we find another temperature? Yeah, I know it's a bit stressful to stand up there and you need some time to think. But I think I would suggest that why not look at the global insulin temperature just at the onset of ignition? So you could use that as well in the results, because that could.
Yes.
It's not perfectly generic, but it's a little bit more generic, I would say. On page 150, we have IMAP in figure 80, and I think you should be very clear about if it's net or gross IMAP.
Ah, okay. On which page?
That was 150, figure 80.
Okay.
Yeah, I think so. Yeah. And I think we have touched upon it a couple of times that on the efficiency, and it would have been very interesting actually to see how efficiency would have changed. This is both a function of the fuel properties and combustion phasing and so on. And it was especially on the alcohol results. So figure 114, page 201.
100.
114, page 201.
201. Yes. Okay.
I don't know if you have this figure in your presentation, maybe.
No, I know. No, I haven't.
Ah, you haven't it. Okay, so is this? Do you have the same fuel energy in the system? I seem to have that.
I check this, and this one of our questions, and the fuel energy is well the same. But after the range for this IMEP is very low, and for a wide operating range, we have to extend it. So for myself, the results are close to the other one, but I must go further into check, and maybe.
Which is kind of interesting. We see that with methanol, you reach almost 2.6 bar indicated mean effective pressure, and with the other fuels you go to 2.4. So if we have the same fuel energy, we have quite a different efficiency of the system. The figure itself also tells us that the combustion phasing, just as you discussed in the thesis, is so important for finding the efficiency. And like the other reviewers have discussed, I mean, together with this ozone generator, we could find you have the data for looking into the system, well, except for, I mean, the gross efficiency of the system, I would say. Okay, I have lots of more questions, but I will not ask any more questions. I'm very pleased with this work. I would say it contains a lot of new information. And you have taken the time not only to just present results, you have been thinking a bit further about it and coming down to a proper analysis of the more fundamental aspects of why things behave in a certain way. And for me, this is just what science should be all about. So I think it's a great thing. Thank you.
Thank you for your comments.
Thank you very much. Professor, continue. Maybe you have a few questions left?
Yes.
They stole you all yours or not? Well,
No, it's okay. So, Jean-Baptiste, let me first start with a very detailed question, and then I will build up to other things. We discussed about alcohol, and one of my first questions was, because actually we want to use that mechanism. The mechanism of Sarati you used was initially developed for butanol. I understand the underlying logic of using the same mechanism for 3 fuels, but do you think it's also valid for autoignition delays for methanol, for example?
In fact, the modeling from Sarati is based on its previous results, and at each time it take so he valid on methanol, he take methanol and include ethanol mechanism and etc. etc. I don't know if it made the modification. I will have to check this point, but this is the process that it seems to do.
And then it was very nice to see that the process towards having really a real live possibility to control cycle to cycle with ozone. But I was surprised that your feedback information was based on the Rankine decree where you have maximum pressure. Could you elaborate on that?
This one or the second? Which one do you want?
Well, the previous you've just shown, you have this feedback. So in the closed-loop control system, you base your control on the alpha Pmax, while most of the time in your results, in your combustion result, let's say, you analyze the combustion phenomena with CA50, CA10, whatever.
In fact, with more research, it will be better to use CA50 instead of this parameter. I only choose this one randomly because the pressure is recording using the pressure sensor, and this is a direct information which do not need any calculation, any estimations for the control.
But I think if you come back to one of the other, later maybe, I don't know, the results where you show the evolution of alpha p max according to your control, so maybe
This one?
Anyway, what I meant is that I think it trims a bit the information since it tends to go to zero. If you increase the ozone, you can show this trend that alpha p max tends to go, you see this decreasing trend going to zero, whereas CA50, for example, would go, yes, this one. You have, I think, more sensitivity with CA50 than with alpha p. But I understand the logic of not using something that recovers information. Then I would like to come to this very nice, so pressure, temperature, and then CA50. Okay, so I think the question, I would like to jump on that because it's very important. The question of previous review was about the intake temperature and or the intake pressure. But could you change that information so that it's another axis, another label on the axis? Instead of intake temperature, I could use something else than intake temperature. I could use, what can I use? As previously said. Do you think it would change the conclusion and your results or not? Do you think the fuel would appear the same way, or this change somehow?
I don't know, it depends on what I consider. So you mean that instead of choosing intake pressure and intake temperature for this diagram, you want to know if I want another temperature in the cycle or another pressure.
Because one of the things you change when you change the fuel is also specific heat. And so you change a bit what happened, even not talking about changing the engine, which is also very important, of course, to show, let's say, engine-independent results. You also change things in the... And okay, you've shown PRFs, but if you put on the same area, PRF versus alcohols, do you think there are things that will change there? What's your indicated guess?
I don't think that if I change this, there is a modification. So if I put another temperature or another pressure, after maybe choose another one would be better to compare the fuel with the other ones.
So as you know, I've made the exercise to put PRFs together with alcohols and other fuels, and you quickly see that they don't have the same orientation. The region they've shown, like between CA50, between 1 and 5, for if you put the alcohols together with the PRFs, you see that the zone, the regions are not made the same way for alcohols and PRF. Could you explain why?
I don't really have enough information to argue on this, and this is on topic on which we work, and I think that we have to discuss on this. I think that we have to include at least a fuel sensitivity and well understand each parameter, which what is the role of each parameter on the fuel sensitivity.
Coming back to this intake temperature, as you know, and you have worked with measured intake temperature of above 200 degrees Celsius, do you think it's a good candidate, a good value to represent what the temperature at the bottom of the center, the temperature you use
then in your, let's say, 0D model to represent the real global temperature in your cycle. So I will reformulate. You measure the temperature in the intake, right? In the intake pipe, you measure the temperature.
Yes.
Do you think that's the right value to use to represent the global temperature in your cylinder?
No. No, because there is some heat exchange with the wall of the cylinder and not the intake pipe, the intake valve. So we have to consider some exchange, heat exchange. So to avoid this, we probably need to set an intake temperature close to that of coolant fluid to limit this heat exchange. That was an improvement that I propose into my post-treatment program.
And then I would like to come back to this 10 bar per crank angle degree. But first, a very specific question. So it's maybe the question is a bit stupid. Why 10 and not 20 or 15?
I have not really a criterion for this. Instead of using this parameter, it will be better to use a ringing index, and it's because with ringing index there is a real definition of a knock.
Right. So can we go back to your slide 23, please? This is just an excerpt of one of the figures you used. So heat release rate is not measured; it's computed according to the pressure.
Yes, of course.
Are those ringing there on the right-hand side? So
this?
Yes. Is that coming from knock? Because I couldn't see on the pressure, but I guess you smoothed a bit your pressure.
Knock on the pressure must be here, something like this here.
Yes.
And I think that this only comes from a filter applied to the in-cylinder pressure signal before the calculation of this.
So you still don't have knock in that condition, although it's really very early in the cycle and quite high in diffusion. You don't have knock there.
No, there is no knock here.
But you are at, I couldn't guess, but I guess around 10 degrees, 10 bar per crank degree.
Yes, for you the slope here is too important, and I must determine knock on this.
So maybe that's a follow-up question on that. Do you think the knock will be depending on the inlet pressure?
Yes.
Knock propensity, and how?
For this, I don't know. I don't know if I increase the intake temperature. Obviously, I can tend towards such a shape of the in-cylinder pressure. After all, I don't know.
And then we need to finish a philosophical question. How can we increase IMP in HCCI? Because we are always talking about sub-10 bar IMP growth. What can we do to improve that?
To improve or increase?
Well,
increase. I inject more energy, so I increase the equivalence ratio, and there is more fuel and more IMP.
You have the constraint of the bar per crank angle degree. You are constrained by your knock limit, right?
Yes. There is a knock limit, so to decrease after I have to include to consider also EGR using the use of EGR.
That's that's all for my question. Thank you very much for your work. It was very, very, very interesting, very broad and in detail, so really enjoyed it. Thank you very much.
Thank you very much, Francesco. Well, before I let your PhD advisor say a few words, I have a general question. So you did lots of experiments. Maybe not enough. What do you think that you should have done that you didn't have enough time to write additional experiments? But if I were giving you 1 more year, what would you like to investigate? And don't tell me a stainless steel tube where
I don't really know. We can go out of this topic or not? No, I think I would like to go further into the understanding of fuel sensitivity.
composition.
Yes, fuel composition. Try to make some experiments with other fuels than that I already done, or another way that I would like to work will be to investigate other combustion modes. So for myself, in my point of view, in the future, we'll replace compression ignition and spark ignition by advanced combustion mode. So I would like to go further into my analysis and understanding of all these low temperature combustion modes, as we call them.
Okay. Thank you very much. And congratulations for your presentation. It was very, very nice, nice slides, everything. So now it's time for the PhD advisor to say a few words.
Thank you, Mr. President. I have no questions. I have just comment. First, I want to thank you for all this job. You integrate in fact the lab during your master internship degree, and you perform many experimental measurements. You install all this ozone generator measurement and so on, and you develop your own code to analyze in fact the incident pressure. So it was a very nice job, and you work a lot. So it's very important to say that. I think Guillaume Deima, the other director, is not here because he's in the commission school of the French Commission Institute when they speak. But I think he appreciated also your work. So it's good for that. I want also to thank the sponsor. And the sponsor is Philip. Of the European Union. And yes, it's now a whole story in fact between the both lab, Prisma and ICA. And we started to study the interaction between the mineral spaces and the fuels since more than 10 years ago. And I think we will continue in fact all this job with another PhD, with a new postdoc, Ida, and I'm sure we will try to have other funding to perform new measurement or new calculations with new ideas. So I think it's really important to say thank you to Philip for the opportunity to integrate us to his years. We have two kind of PhD students in the lab, foreign and French one. And actually French one is from Normandy. But it's not France. Sometimes it's very difficult to manage this kind of student because they need to, they have their own character, and sometimes it's really difficult. It's a joke. And for your future, I really appreciate in fact your presentations and the written of the presentations. And for the future, I think that you can use other fluids to increase your engine speed. So switch from beer to Red Bull or something like that. And because we need to use them. We ask for it. So again, it's a joke, but we spent a very lot of time together with the other team around in fact this work. And just to finish, ACCI for everyone. In fact, we use this kind of engine ACCI just to study fundamentals of autoignitions. It's really the idea. We haven't any other machine, but we use this kind of engine like a rapid compression machine, a multi-compression, in fact, rapid compression machine. It's really the idea because we want to separate the different phenomena. Sure, we know that to apply HCI, we need to add new things, perhaps a direct injection, perhaps a DCI, perhaps new other concept. But it's the first step for all these other mode, compression mode. So it's very important to know that, in fact, that I'm agree that the efficiency is not good. I'm agree that, in fact, the pollutant emission is not good. But it's not the goal of this work. Really, the idea is to have a beautiful background for the pleasure, for the new concept. And so I think and I hope that we can prove it for the next year, the next step. So thank you again for your work, your presentations, and I think we can say that you will have a very nice future for your research career in the next months.
Okay, thank you. So now the committee will debate. You have a room for us?
Ils vont débattre et ils reviennent après, ils annoncent le résultat.
Non, mais c'est juste que je sache si je démonte ou pas. Mais okay,
bon, je sais pas si t'as...
Ok.
Ok.
Bon. Ça. Du coup, ton micro est toujours allumé, tu feras gaffe.
Ouais, je sais. Attends. Bon, de toute façon, t'as le micro d'ambiance, là.
De quoi? Bah non, j'ai ton micro là, parce que celui-là, il prend, mais il prend pas...
Ouais, t'as pas de...
Donc, t'as été filmé?
Ouais.
Filmé, retransmis
C'est transmis où?
sur Internet.
Ah bon?
Et enregistré, quoi.
Non, pas tout.
Non, je suis le premier, je suis le cobaye.
Je sais pas si on a vocation à toutes les faire, mais...
Bon, je pense que pour nous, je pense que ça va...
Ça va dépendre dans la demande, en fait. Mais,
Merde, qu'est-ce que j'ai fait?
Okay.
Hop.
Bon, bah, félicitations.
Voilà.
C'est pas fini, mais c'est fini.
Putain, Martin Tuner, j'avais du mal à le comprendre. Et Louis aussi. Louis, il parle trop lentement.
Mais tant mieux.
Ouais, mais non, du coup, j'avais pas su. En fait, je perdais le fil de ce qu'il avait dit avant. Parce qu'il était trop lent. Il est quelle heure? Il est 5h. T'as vu, je l'avais dit, il y en a pour jusqu'à 5h.
On s'en rend pas compte. Bah oui, mais
enfin, en même temps, ils ont commencé à 14h30. 2h30. Putain, on a fait... Attends, à 14h30
toutes les questions.
Putain, ils m'ont fait 1h... 1h15.
Il va te faire travailler, des gros. J'ai compris.
De quoi?
Il va te donner plein de trucs à faire.
Putain, Dibble. Bon, j'ai mis plein de rouge. Ok. Alors, Dibble, donc pour toi qui était à gauche de Philippe, donc Philippe qui présidait, donc c'est C'est le directeur de recherche au CNRS qui a financé toute ma thèse, donc sur un projet. Comment? Oui, c'est tout le temps, il n'arrête pas. Ouais, je comprends pas tout.
Comme ça, on entendra leur.
Donc tout est prêt.
Ok.
Enfin, tout est prêt. Audrey m'a aidé. Bruno m'a aidé.
Qui?
Bruno.
Bruno t'a aidé?
Oui, il m'a aidé, il a coupé les cakes. Et ils sont occupés de la tireuse.
Ça, c'est le plus important.
Et ils sont occupés de la tireuse, et ils se sont occupés. Ils ont mis l'étal, on en a rajouté une.
Je sais pas, vous avez laissé ouvert ou pas?
Non, je crois pas. J'ai validé.
Tiens, je te laisse. Non, mais il y a Fabrice. Tu veux d'abord de Fabrice? Non, mais je te laisse. Tu laisses la première porte ouverte. Tu la penses.
En fait, les petits fours, il faut les faire chauffer aussi.
Ah bon? Tu l'as fait?
Bah non, j'ai dit que j'allais le faire quand
Ouais.
avec les préfous.
Ouais, ok, ça marche. Ça marche.
Je t'ai coupé les tartes, je les ai sorties. Je vais les sortir. Bah oui, du coup, Pierre m'avait ramené sauf les méchadins et puis les radis, donc j'y suis retournée, je suis allée les chercher.
Ouais.
Les tartes, les cakes et tout ça. Et c'est pareil, je sais pas comment je suis. Je t'ai fait les 5 000, je sais pas.
Tu m'as fait
les 5 000.
Oui, il faut les faire tous.
Je suis beau.
Tu les as coupés comment là du coup? Ils sont comment?
En quart. En gros, ça mêle.
En 4, ok.
On va recouper en plus petit. Ça me fait peur. Et il me dit quoi? Je dis mais non, mais t'inquiète pas, mais non, il me dit j'ai pas peur pour le moment, j'ai peur pour te dire. Oh, je regarde pas. Tu peux le garder dans ta sacoche? Là, j'ai pas de poche.
T'as pas de poche?
Là, j'ai des poches, mais non. Alors, moi, j'étais bien. Je me suis recoiffé les cheveux. Et puis après, je vais traîner le pays.
Je vais laisser tout ce qu'il y a là-dessus. Après, je ramasserai.
Comme toujours. Oui,
je donne ça à Pierre.
C'est quoi déjà pour le portrait? Quand je veux le truc qui t'explique, il ne le donne pas. Quand tu veux pas le machin qui t'explique, il te le donne. Ah, comme ça. Non, mais tu veux qu'on se mette où? Bon, il est parti.
Je sais pas, tu veux.
Bah, je sais pas. Hein. Ah, voilà. Alors, attends. Non, en fait, non, c'est pas ça, c'est que je me souviens.
Il est tout retourné, hein.
Je ne sais plus si c'est en A ou en B. Ça va.
Merci. Beaucoup.
Félicitations.
Welcome.
Bravo, félicitations.
Merci beaucoup.
Bon, malgré tout, il y a quand même des petites corrections. Tu verras, et professional people have some